So let's get started. Last time we talked about limits of infinity. I mentioned a few things we can do with those limits. The ways they work, right? Let me settle all these in. Here, here. So limits of infinity, right? What we talked about was if we have the limit as x goes to infinity of some kind of fraction, right? X to the squared minus 2x plus 1 over 3x squared minus 5x plus 7. But the only thing we care about is the biggest exponent. We talked about that. Only the biggest exponent matters. Talked about that. And so you can cancel out all the other stuff that don't matter, and then you kind of just focus in on the parts that do, like these squareds. And the second thing you can do, second thing we kind of talked about, right? Only the biggest exponent matters. Second thing is you can kind of plug in infinity or negative infinity and simplify. Like do some canceling, do some squaring. So for example, in the squares here, if you plug in the infinity, both the top and bottom would cancel, and you'd get 1/3. X squared would cancel with the x squared, and you'd get 1 over 3, and that would be your limit. Talked about things like that. And then we made sure you simplify by, if it's negative and positive, figuring out negatives and positives. A couple other features of things that you need to worry about, like for example numbers 5 and 6, right? These square roots. How do I deal with the square roots? And I didn't talk about that, so let me bring that up right now. If you have a limit as x approaches infinity of, let's say you have x to the third power plus 2x to the third power plus 7 divided by a square root of 9x to the third power plus 7x squared. Something like that. With square roots, the same rules apply as before. Same rules where the only one that matters is the biggest exponent. So I don't need to worry about that 7. I don't need to worry about that. Okay? With square roots, again, only the biggest exponent matters. And what you see is when you do this canceling, what will happen is this will become the limit as x approaches infinity of 2x cubed over the square root of 9x. Oops, I'm sorry, not cubed. Let me make this not cubed. Make this to the power of 6. Okay. What's going to happen with square roots is that you do the simplifying. So I know what the square root of 9 is. I know the square root of 9 becomes a 3, right? So it becomes 2x cubed over 3. Square root of 9 becomes a 3, right? With the square roots, you also simplify. With exponents, the 6 here, a square root, like for example, if I had the square root of x to the 8th power, remember that a square root is the same as a rational exponent. Square root means I have the power of 1/2. Did everybody know that? Square roots are fraction exponents. Remember, there's like an invisible 2 here. Always there's like an invisible 2 in the square root. So the square root of x is the same thing as saying x to the 1/2 power. So if I have a square root of 8, that's the same thing as x to the power of 8 over 2. So I'm like dividing the exponent in half. So this becomes x to the 4th. So you divide the exponent exponent in half. That's what square roots do to exponents. And so x to the 6th power is really x to the 3rd power. Square root of x to the 6th power, the square root cancels with the power, and it cuts the power in half, cuts the exponent in half. Because of this rule with fraction exponents. Square root is really a fractional exponent. This is the true form of a radical. So the square root of x to the 8th power is x to the 8 over 2. 8 because of the 8 power right here. The first part is the top of the fraction, right? The regular exponent is the top of the fraction. The radical part is the bottom of the fraction. So we have a fraction, right? We divide 8 divided by 2, because there's a divisible, 2 square root, and that becomes x to the 4th power. Same thing. So you divide your exponent in half. That's what square roots do, right? And again, we can ignore every other piece of the radical. We don't care about them. The only ones that matter is the biggest. So the radical here cuts the exponent in half, and now we have a regular situation, where I can cancel the cubes. My answer is going to be 2/3. So the radical is there, but the only thing it does is it does a square root of the number part. It does a square root of the number, and it cuts the exponent in half. So that's one thing that's maybe a little trick that I didn't talk about very much last time. Hopefully that clarifies things. One more piece that's important to know, one more step that's important to know, let me bring this down a little bit more, is what if I have the limit, what if I have the limit as x approaches infinity of something like sine of x? How does this work? Remember, the graph of sine is like this. And Parisot has an idea that the limit does not exist. Why? Can you explain why do you think this is dne as we go towards infinity? Parisot says the limit doesn't exist. Why is that? Maybe he's... Yes, thank you. Oscillating, yes. So it is the limit of things like sine x does not exist because x oscillates, that's how you spell it, between two values forever. X oscillates between two values forever. It never focuses in, never focuses to one spot, right? Never focuses to one spot. This is really bad. So if you have a graph that's doing that variation, and usually it'll be like things with sines or cosines or tangents, things like that, any oscillating function, any trigonometric function, chances are good that it's going to be a dne. Chances are good. Right. So those are the two other situations that we have, our square root situation and the oscillating situation that I didn't talk about last time. We were talking about limits of infinity and end behavior, right? So the end behavior of this sine graph, right? There is no end behavior. It keeps going forever, right? It always bounces back and forth. There's no end behavior. It keeps going forever. It keeps oscillating forever. So it never focuses in on one spot. Even a function like x squared focuses in, we know it's not bouncing between things. It's going to one spot. It's going to infinity. It's always going up. It's consistent, right? Even things like x squared. So if I did like the limit as x approaches infinity of x squared, it's consistent in its direction, right? Is consistent in its direction. Consistent in direction. It's always going up. Goes up forever. And that's why we can say this limit is infinity. That's why we can say that limit's infinity, because it goes up forever. It's never going to go back down and be something different later on. So when you oscillate, that's where you have a problem. If you're always constantly changing, that's the problem. When you're consistent, that's when you can find a limit there. Okay? Questions about that? Jessica, I see your question about number 4. Let's dive into these then. Let's dive into these. So again, a little bit of situation here. We have limits of oscillating functions. We have square roots now we know how to do. So those provides a little bit of clarification on some of these questions. So let's get into it. Let me zoom. Let's talk about these problems here. Number 1. So we have ABC, limits of infinity, negative infinity, and any asymptotes we want, any horizontal asymptotes. Number 1. What is the limit as x goes to infinity of this problem here? In the chat, type in the chat what you think your answer is. What do we know this? For number 1. For number 1. For number 1. Number 1A. Let's start on this question right here. What is the limit as x approaches infinity? So we have, looking at our problem, we're looking for the biggest exponents. So I can ignore the 1 and the 13. I could ignore the 3 and the x and the other x. I could ignore this x squared because there's a cube on top. And my bottom biggest is x squared. Yeah. So really I have the limit of 3x cubed over x squared. So infinity over infinity, well that would be a 1. Alright, so I've got infinity over infinity. Jessica says positive infinity. Anyone else got any answers? How do we know which it is, right? So remember, with these, with these exponents, we know we can cancel them, right? I have 2 x's on the bottom, 3 x's on the top. I can cancel these 2 x's with 2 of the x's here, leaving 1 x up here. Or if you like, you can think about canceling infinities. And so we have 3 times infinity on the top over 1, and that's going to be infinity. When we have a bigger number on top, when infinity is on the top, yeah, it's going to become positive infinity. What about the limit as x approaches negative infinity? Same thing, I have 3x cubed over squared. If I limit as x approaches negative infinity, just thinks negative infinity. So again, the same thing, right? Let's really carefully evaluate our options here. Cancel the squared, cancel 2 of these. I have 1x on top. So I'm going to have 3 times negative infinity over 1, which, yeah, the negative makes it negative infinity for this one. All right. So you're looking at the exponents, you're checking out what's left over after you've canceled everything you can cancel. What's left over? Plug infinity or negative infinity into those x's and see where it ends up. Does it end up positive? Does it end up going up forever? Or does it end up negative where you go down forever? Part C here, there is no horizontal asymptote. And I don't really want you to worry about slant asymptotes. Don't worry about those. Since we're going to infinity and negative infinity, there is no horizontal asymptote. And that would be the answer for number 1. Good, everybody? Making a little bit more sense? Clarifying our infinities. Think about how all these work. Let's try number 2. Erase myself here, get a little bit of room. 2a, again, we're looking for the limit as x approaches infinity. For number 2a, we're going to cancel stuff, and I'm going to have a squared and x cubed left over here. So really I'm going to have 4x squared over 2x cubed. And again, I can cancel some variables. The x's here, cancel with those. So I have 4, let me do this in a different color. So I'm going to have 4 over 2 times my x is left over on the bottom. There's an infinity on the denominator. So 2 over 4 over 2 times infinity. What does this get to as the denominator goes to infinity? What answer is that? What do you think, everybody? 0. Yes, indeed. When you have an infinity in the denominator, your answer becomes 0. When you divide by infinity, it becomes 0. Very good. All right, what about part B, the limit as x approaches negative infinity? X approaches negative infinity. The same thing, 4 over 4x squared over 2x cubed. That's it. Oh, goodness gracious. 4x squared over 2x cubed. Again, I'm going to cancel. And you can do all of this in your head, by the way. If you look at the answer, if you look at it and you see, oh, immediately I notice, right? You don't need to go through all these steps. I'm just showing you all this stuff, all this work. You don't need to show me all this work. If you see this and you see, oh, I have a squared here, a cubed here, bottom is bigger, bam, I know the answer is 0. Just get there. Just go there. That's fine. So this is going to be 4 over 2 times, but if it helps you to like clarify like this, maybe write it out a little bit, help you out. So I have 4 over 2 times negative infinity, negative on the denominator. So what's this answer going to be, everybody? 4 divided by 2 times negative infinity. I'm getting negative infinity on the bottom. Is it still 0? Should it be negative 0? Negative 0? No, there's no negative 0. It doesn't exist. What is negative 0? That is, by the way, that is a profound question. What is negative 0? Yeah, because infinity doesn't matter if it's positive or negative. If it's an infinite number in the denominator, you are going to make a 0. Exactly. Exactly, Angel. Because infinity is in the denominator. Doesn't matter positive, negative. There's no such thing as negative 0. It's just 0. It's just 0. So for part C, what's our horizontal asymptote? We do have one. And the answer is y equals 0. When the numbers are the same number means horizontal asymptote. And if you imagine the graph of this, you know that on the 0 here, there will be an asymptote that kind of goes, I don't know, like this maybe, and then like this, and then like this. It might have asymptotes as well, but it's got the horizontal asymptotes where it goes left and right. Here is your horizontal asymptote, right, where the graph kind of settles out right at 0 because the bottom is bigger. And if you understand that pattern, you'll see this happen again and again. Every time the denominator is bigger, your horizontal asymptote will be along the x-axis, the equation y equals 0. Whenever you have a rational function, your denominator is bigger, you'll have this horizontal asymptote, this end behavior of reaching towards 0, getting smaller and smaller forever, because we're approaching infinity. And when you divide by infinity, you get a 0. Right? Isn't it wonderful how math fits together? All right, everyone. Let's try number 3. Number 3, we've got this one here. Again, the limit as x approaches infinity. This one here. Again, I can cancel my non-important pieces, the 1 and the 4. I have x and x. So it's going to be 3x over x. And then what? Well, now they're the same on the top and the bottom. Since they're the same on the top and the bottom, I cancel this x, I cancel this x. What's my answer, everybody? There's like a 1 here. What would this limit be? Alejandro, I'm going to call on you. What's my answer for this one? Alejandro? You there, Alejandro? Your mic's not working. I don't know what's going on. Tell me, what do you think the limit is as we approach 0 of this equation here? What do you think our answer is? There you go, Alejandro. Very good. The answer would be 3, correct? Because you cancel the x's, you get 3 over 1. That answer is 3. Thank you. Good job. Let's try the next one. Limit as x approaches negative infinity. I'm going to call people that haven't been talking. 3x over x. Let's see. Kimberly, what do you think the answer is for this one? As x approaches negative infinity, what would the answer be here? Negative 3? So remember, we're plugging in negative infinity. We have 3 times negative infinity on the top over negative infinity on the bottom. Positive 3. Yes, very good. Because these two negatives, negative over negative, these are going to cancel each other. These negatives go away, so it's still only just 3. You have to be careful with these negatives. Yeah, write it out. Again, write it out. Think about how they cancel, how they interact with each other, these negatives. Part C. Michael, what would be, or do we have, a horizontal asymptote in this equation? What do you think? What would the horizontal asymptote be, or do we not have a horizontal asymptote in this equation? Michael Jones. No horizontal asymptote? You don't think so? Yes? Okay. What do you think the horizontal asymptote is? At y, yes. Thank you. Exactly. We have the same number here, right? So that means that y equals 3. Very good, Michael. Thank you. Horizontal asymptote at y is equal to 3. So in this graph, if you want to look at it, right, you imagine 1, 2, 3. You imagine there will be a dashed line here up at 3. And your graph would look something like this. This vertical asymptote. Anyone want to guess where this vertical asymptote might be? Anyone have any ideas where this vertical asymptote is? Look at the equation. Look at the equation here. Not 3. Nope, not 3. Where's the vertical asymptote? Jessica got it. Look at the bottom here. Remember, vertical asymptotes happen when the denominator is 0. So this x minus 4 means my vertical asymptote will be at 4. Very good, everybody. Nice. All right, let's keep going. I want to stop. I want to do this for 10 more minutes. I'm going to do these free response ones, then I'm going to maybe leave you for the multiple choice ones. How can I erase more than this at once? Let me see. Can I grab a section? Let me see. Grab all this. No, I don't want to do that. I just have to do it bit by bit. Okay, fine, whatever. Number 4. Limits as x approaches infinity and negative infinity of sine 3x over x. What do we think that's going to be? Jessica, you had an idea already for number 4. Can you tell me about it? What do we think? Limit as x approaches infinity of sine 3x over x. Harry said Danny. Yeah. Idea was because, oh, interesting. Stop it. So, right, how do we know? How do we know whether it's going to be going up forever? Let me first take a little bit of a side. Do we remember the limit as x approaches 0 of sine 3x over x? Do we remember the rule for that? Just a quick little refresher. This function is special if we approach 0. If we approach 0, the answer was we kind of ignore that and just look at ignore the sign, just look at the numbers, and we're going to get 3 over 1, which is 3. So the limit of 0 would be 3. But let's take a look at the graph. Can I graph this? No, let me see if I can change this over to a graph, everybody. Hold on. Go to, where is my, hide this, open this up. Go back to a website. I want to be able to look at our graph. If you're ever lost and confused, doing the calculator is a great way to help you identify what's going on. Y equals sine of 3x over x. So let's take a look. So we have some functions, right? They're kind of bouncing back and forth. Interesting. Interesting. What's happening here? If I were to zoom out, look at the very edges of the graph here and here. What does it look like? Does it look like it's bouncing up and down forever? Let me zoom in to a section here. Let me go way far out to like a huge number. Really big number. What does it look like is happening here for the graph? Well, we'll get to that. So here's the thing. It looks like, okay, it's going here. It's getting kind of like really close to 0. Let me go even bigger. Let's go huge crazy number. Let me zoom into this huge crazy number and get real close to the graph here. I just want to use this as a visual, right? So you see what happens is the function gets really I can't zoom in anymore. It's the most zoomed in I can get. That's all I can get. So as it gets bigger, we think it should bounce up and down forever, right? But what happens is it's kind of it's bouncing big, and then it gets a smaller bounce, then a smaller bounce, then a smaller bounce, and a smaller bounce, and a smaller bounce, and it's kind of focusing in on this particular spot. So you see the bounce is big here, and then it gets a little bit of a smaller bounce, and then a little bit of a smaller bounce, and a little smaller. And over time, those bounces get smaller and smaller, and it kind of focuses in on a spot. It looks like this is getting closer and closer to 0. Right? It looks like the limit should be 0. But how do we tell? How can we be sure? Well, let's look at what we know. Where am I going? Oh, hold on. Let me go back to the whiteboard. How can we know? How can we know for sure what this is going to be like? Erase this. So if I were to plug in infinity into this situation, as per usual, we always want to try plugging in. This is going to be the sine of 3 times infinity, goodness gracious, times infinity over infinity. Okay, over infinity. Now this part up here oscillates forever. But what happens when we have this part down here, infinity in the denominator? What happens with that? Infinity in the denominator means what's happening? Means our function goes to 0. So the question is like, which one's more powerful, right? Oscillating forever or going to 0? And in these situations, turns out this bottom one wins. The denominator takes over the situation. When we divide by infinity, that answer is always going to get to 0. So the sine 3x over x is not going to oscillate forever. You're going to get a 0. It's not DNE. It's not positive infinity. It goes to 0 because we divide by infinity. So when you plug in those infinities, always pay attention. No matter what's on the top, if you ever divide by infinity, you will get a 0. No matter what's on the top. Well, except if you're canceling. That's different. Okay? I'm at a minus 1,000 points from me. Apologies, everybody. Good job. So that's going to be 0. So we know the limit as x approaches infinity is 0. Does it work the same for negative infinity? Yeah. Sine 3x over x. Again, we're going to infinity and the denominator. That is also going to be 0. Exactly. Positive infinity, negative infinity doesn't matter. Both those infinities going to make a 0. So if you have an oscillating top but a 0 denominator, infinity denominator, that infinity denominator is going to like take over and become a 0. So that means our horizontal asymptote, part C, horizontal asymptote, we have y equals 0. Now wait, I thought an asymptote meant you could not cross, right? Mr. Mitchell, I have a complaint. I'd like to file a complaint. I would like to file a complaint, please. I thought a horizontal asymptote meant you could not touch it. So why does this sine graph constantly be going touch, 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 touch? Why is it doing that? How is it touching this asymptote? Well, it's not that it can never touch. What an asymptote means, asymptote only cares about end behavior near infinity. An asymptote is just a number that you are getting closer to. It doesn't matter if you get closer from the top. It doesn't matter if you get closer from the bottom. It doesn't matter if you get closer in an oscillating way. You're getting closer to this number no matter what direction you're coming from. Asymptotes only care about end behavior. When I was taking AP Calc in my high school, many years ago, many years ago, I had this AP Calculus teacher, and I'll never forget this in class. She was 90 years old, Miss Kalman, and she said, "Now, class, when you're looking at a limit of infinity, you're only think of end behavior, everybody." And she would point her thumbs out like this, and never forget that. End behavior. That's what matters with infinity. Infinity only cares about the edges. It doesn't care about the middle. It can touch the asymptotes all day long. We don't mind. But the ends are reaching this number. The ends are reaching that number. Okay? Oh, thank you, Perry. All right? All right, so that's number B. Number 4. The red part. The red part says oscillates forever. Forever. Whoopsies. Oscillates forever. So the denominator, here I'll just write the denominator wins. Denom wins. Denominator wins. More powerful in the bottom here. All right, I'm running out of room. I'm going to skip number 5 because I have no room. Let's do number 6 just quickly here, and then I want to get to our little practice that we have. Number 6. Part A, limit as x approaches infinity. We've got our situation with a square root. So again, when I do this, I can ignore everything but the biggest exponent. So the 1's going to go away, 4 is going to go away, squared's going to go away. This 6th power, I'm going to simplify this, right? So I'm going to get 5x cubed over square root of 3. There's no square root, so I have to keep the square root of 3, but the exponent, I can change. 6 becomes x cubed. Okay? I don't like my fingers on. So when I do my radicals, right, when I do the radicals, I have to make sure I am doing the radical part of the number too, and sometimes I have to leave the square root part. It doesn't get a number. That's okay. So what do we think this is going to be? Well, my radical, my cubes are the same, same on the top and the bottom. I can cancel that, and so my answer for this one is going to be 5 over root 3, which is perfectly fine for a number. It's some decimal, I don't know, it's 2.3156, who knows. But we leave it 5 over root 3. That's your answer. That's your value for that limit. Because you canceled all the things you need to cancel. We're going towards infinity, so we don't care about the bigger numbers. We don't care about the small numbers, only the biggest. Only the biggest. What about the limit as x approaches negative infinity? It's going to change. 5x cubed over root 3x cubed. Same thing. X cubes cancel. I don't care if it's positive or negative. It's still 5 over radical 3. And so my horizontal asymptote, part C, is y equals 5 over. Okay. Oops. So does that help, folks? Talk about limits of infinity. Talk about square roots. And we talked about what happens with oscillating exponents, oscillating limits. If the top oscillates but the bottom is an infinity, if the bottom's infinity, that's where it becomes 0. All right, there's one more thing I wanted to mention in this situation. I'm going to head to the next page. Yeah, everybody? So we went over these limit things. There's one more sort of topic to talk about. Let me go to the next page. These multiple choice sections, and I want to do these last ones, 13, 14, 15. I want to talk about these. So I want to talk about the limit as x approaches infinity of something like 2 or e, whatever, it doesn't matter, 2e to the x, or 2 to the x, things like that. Okay. Exponential equations. Exponentials. So exponential equations generally have a look that's like this. This is a to the power of x, where it has this horizontal asymptote, but also goes to infinity. So there's like two sides. Exponentials have two sides to their part, right? This side goes to infinity, and this side, negative infinity, goes to 0. So exponentials have different answers for different directions of infinity. Positive infinity is going to be going to infinity. Negative infinity is going to go to 0. And that's the thing to remember, right? Positive infinity goes to infinity. Negative infinity goes towards 0. For exponentials, they have this double-sided situation. Okay? So that's the thing you need to remember for these answers here. So if we did like, which one? Let's look at a simple one. Let's do, the limit as x approaches infinity of 2 to the x over 5. Okay. In this situation, same things before, we're going to imagine plugging in infinity. 2 to the infinity over 5. I know that this top part here is a positive infinity. Right? This is my positive infinity. My exponent is positive. That means it's going to be infinity. Positive infinity, right? My positive infinity goes to infinity. So if I have an exponential, a 2 to the power of infinity, positive infinity is going to go to infinity. But if I were to take the limit of this one as x approaches negative infinity of whatever, e to the x, doesn't matter, over 5, I'm going to get e to the negative infinity over 5. Negative infinity, my negative infinity goes to 0. So this is going to be equal to 0. Because it's like you're saying 0 over 5. 0 divided by 5, 0 on the top of the fraction is still going to be a 0. So exponentials have this double-sided limit. You need to be aware. Are you going to the positive infinity side? Or are you going to the negative infinity side? Sometimes they throw negatives at you, like in number 13. Let's do this one together. Limit is x approaches infinity of 2 to the negative x over 3 to the x. So if I plug infinity in here, I'm going to get 2 to the negative infinity over 3 to the infinity. So this is like a little complicated. I'm going to get like 0 on the top and infinity on the denominator. What's going to happen here? What do we think this is going to be resulting in, everybody? 0 on the top, infinity on the bottom. What's the situation? What's going to happen in this situation? People think 0. Yeah, look at the choices, right? Do you think it's going to be negative infinity? No, probably not, right? Probably not that one. A 1? I can't really make a 1 from that. Might kind of be infinity. Probably not going to be 2/3 because the 2 and the 3, right? That's not. So it's maybe like 0 or maybe infinity. But yeah, if we look, remember 0 on the top and the infinity on the bottom. Both of those things mean my answer is going to be 0, right? The 0 on the top gives me a 0. Infinity on the bottom gives me a 0. Because any number divided by infinity is 0. Yeah, well, except if I had infinity over infinity, that would be 1. But basically, yeah, any number divided by infinity. Good. What about 14? Plugging in infinity here, I'm going to get 5 plus e to the negative infinity over 1 minus e to the negative infinity. Because the negative sign here is my negative in front of my x's. Be aware, make sure you're going towards the right thing. 5 and 1 I don't care about. Those are too small. E to the negative infinity. Let's see. That's going to be... where's my pen here? Let's do this one. E to the negative infinity is going to be, so that's like 0 on top over negative 0 on the bottom. What do we think that's going to be? Uh-oh. I don't have an answer of 0 here. 0 is not one of my choices. What do we think is going to happen in this situation? Negative infinity? 5, negative, which ones can we cancel? Probably the 5 and the negative 5 I can cancel, right? Well, actually, oh, you know what? You know what? I was doing this wrong, everyone. I was doing this wrong. I'm not going to cancel the 5, and I'm not going to cancel the 1. These are very important. Because this is basically saying I'm going to get 5 plus 0 over 1 minus 0, which is 5 over 1, which is 5. Huh. Interesting. Interesting. Why do the 5s matter for this, but they don't matter in those other situations? Well, in the other situations, you were adding it to infinity, right? If I was doing 5 plus infinity over 1 plus infinity, the 5 and the 1 wouldn't matter. But because the numbers, these e's are going to 0, because these e's are going to 0, my exponents are going to 0, the 5 and the 1 really do matter. So it's always good to look at every piece of the puzzle here. Because e to the negative infinity goes to 0, the 5 and 1 do matter. Okay. So last one, number 15. The limit as x approaches negative infinity. So I'm going to get 5 plus e to the negative infinity over 1 minus e to the negative infinity, which is 5 plus e to the infinity over 1 minus e to the infinity. Any ideas for this one? Five plus e to the infinity. Okay, we don't have a 0. Any ideas for this one? Well, let's again plumbers. Let's get the values. 5 plus what's e to the infinity power? Well, that's going to be infinity. Over 1 minus e to the infinity, that's going to be also infinity. So in this case, do the 5 and the 1 matter? In this situation, does 5 and 1 matter? Five plus infinity, is that going to be a number that I care about? 1 minus infinity? No, yeah, the 5 and the 1 don't matter anymore. They're too small to care. In this last situation, when they went to 0, it mattered. This situation, going to infinity doesn't matter. So I have infinity over negative infinity. Infinity divided by negative infinity. And what do we know about that? How do we deal with infinity over negative infinity? What can I do about that? Infinity divided by negative infinity. Well, just like variables, infinities can cancel. So it's kind of like I'm canceling this infinity with this infinity. What am I going to get? Positive over a negative means my answer is going to be negative 1. Infinities can cancel just like a variable. We saw that before when we had our x to the power of 3, x to the power of 2. You were canceling the infinities there. Same thing here. When you plug in your steps to the situation, plug in your infinities, plug in infinity, simplify, and then solve. Simplify by meaning like if we have e to the infinity or 2 to the infinity, it's infinity. E to the negative infinity, 2 to the negative infinity is 0. Simplify like that. Cancel out anything you want, anything you can. Cancel out your infinities, cancel out your variables, and see what you're left with. In this case, we're left with a negative 1. Because I have a positive over a negative. 1 over negative 1 leaves me with negative 1. Easy, right, everybody? This is like baby stuff, no problem. All right, a few answers, a few problems done together. Try some of these. Make sure you get this into me by tomorrow. Last thing, we have like 2 minutes left. I guess I don't have time to do this in class. I'm going to stop sharing my screen for a second. Everyone got everything they need? All right. I'm going to stop the recording and post this to Schoology.